Okay, let's get started. So today we will keep talking about buffer overflow. Last week I showed you the share code. That's probably the first share code you have seen, and you understand the logic, you understand every instruction of that, and in theory you know how it works. So today, but last week I told you that share code doesn't really work on our platform. So today we will say why it doesn't work and how do we fix the problem, and other share code we can develop to get the flag in the class. So we will go to an example directly today. So this is the buffer overflow return 4. We actually will use this example a lot throughout this semester. We use it for buffer overflow. We also use this in return-oriented programming. So this program, very similar to what we had before. We have the only difference is the buffer size. Here I make it larger, and later you will say why I make it larger. But it doesn't have to be this big. Okay. So we have the main function. Main function calls val foo. After val foo, main function calls printf, IPT the full. The val foo has a local variable buff. At C code level, we say it's 40 bytes, but this is only at C code level. The compiler may give several more bytes there. Then after that, there is a getting input from std in to buffer. Then this function returns. So the difference between this one and the previous challenges we worked on is this one doesn't really have a print flag function. So all the previous challenges, there is a print flag function. You overflow the return address of the val foo and hope it returns to the print flag function. However, in this program, there is no such a function. Okay? So instead, what we want to do is we want to inject our own code into the process. Then we can return to that code. And that piece of code, obviously, it will print a flag for us. There are many ways to do that. We are going to say 2 different ways to do that. A little bit on the disassembling this program. At this point, this is the 5th week, and I expect you to be quite familiar with something like this. So when you look at this program, you first look for there is a function call. That's a function call to gets, and gets only takes one parameter. For 32-bit, which means that parameter will be pushed onto the stack. So from this call to gets, we move backwards to say there is an instruction push EAX, push something onto the stack, which means EAX has the address of the buffer. Then we keep going backwards and say the EAX value is EBP minus 30 in hex, which means the address of buffer is at EBP minus 30 in hex. That's obviously a relative address, relative to EBP. The value of EBP, we don't know. We only know that at runtime. Which means in this case, even though the C code level, the C code asks for 40 bytes of buffer, the compiler actually gave us 48 bytes. 30 in hex is 48 in decimal. It actually gave us 48 bytes. So last week, we already saw the share code. So the share code I showed you was only 20 bytes, maybe 28 bytes, but the last 3 instructions was for the exit system call. So if we remove that, it was 23 bytes of share code. So technically, we can put that share code at the beginning or in that buffer, because that's where we can input things, right? Whatever we input, we're putting in the buffer. Then we can share. So so far, we have been just putting garbage in the buffer because we're not using anything in that buffer. Now we can put share code directly there. Then we overwrite the return address, and we make the return address point to the beginning of the share code. Then when this function returns, the CPU will start executing from the beginning of the share code. That sounds perfect, sounds very easy. The problem here is this return address is an absolute address, right? Previously, all the return address you overwrite, those are absolute address. But here you don't really know what is the absolute address. So far, you don't know where the share code is. One way to increase your chance is to add some NOP instructions at the beginning of the share code. So when you overwrite the return address, when you let the CPU jump to a location, you don't have to jump at the very beginning of the share code. You can jump to anywhere on that NOP sled. So NOP is no operation. So in Intel architecture, there is actually an instruction to do that. That's a NOP instruction. Of course, any other instructions that doesn't really do anything, it can be used as a NOP instruction. Some architectures, they do not have a NOP instruction, but you can use any other instructions as long as they do not affect what you are doing as a NOP. So if we have a huge NOP sled, you only need to jump to the middle of that NOP sled. Then the CPU will keep executing instructions that do not affect anything and eventually go to the share code. So your share code can execute. So if you have a big NOP sled, the chance for you to succeed will be much higher. However, in this case, we only have 48 bytes here. So the share code already take like 23, 28 bytes. Then your NOP sled can only be 20 bytes, something like that. So it's still very small. So another approach is we do not really use this part, okay? We put the share code and the NOP sled at a higher address, higher than the return address. So here we have 48 bytes. We just waste that. We don't put anything useful there, just garbage. Then we overwrite the return address. Then we put a huge NOP sled there. Could be 2,000 bytes or even bigger. Then we have like 20 bytes of share code. So the chance for you to land on the sled will be much higher. That's the approach we are going to use, right? We want to use the approach to find the return address, or the return address basically is where we put our share code. So if we debug the program, usually we can have a rough idea where it is, not necessarily exactly where it is, because when you debug the program and when you run a program, the stack will have different things there. Okay, so the address will not be the same. Also, a lot of hacking involves a lot of guessing because you just don't know. Sometimes you cannot even debug the program. If, let's say, you are hacking a remote service, the only interface you have is to send some message to that service and say whether it crashes or not. You cannot download the binary of that service. You don't have the source code of that service. So that requires you to do a lot of guessing. So we have 3 different share codes to use. And the first one is actually the one we discussed last week. A simple version of that one. This one, we do not make the exit system call. So basically, this share code will set up the registers, then make a system call. In the register, we will have the program we are going to execute. In this case, is a shell, and we want to use a default shell, the /bin/sh. So let's see how we can get a shell out of this. Like I said, this one doesn't really return you a root shell, but it does give you a shell. But with this shell, you will not be able to get the flag. Let's start from here. How do I copy this? Okay. So this is buffer overflow 4, return 4. Overflow return 4, 32-bit. So first, let's do a reverse engineering of this program. So this is Overflow. You already saw the source code of this, and the binary code looks like this. The buffer is at EBP minus 30, 48. So imagine how you will craft this this exploit. First, you will have 48 bytes of garbage to fill the buffer. Then another 4 bytes to fill the saved EBP. That's why we have 52 bytes of garbage there. Then after that, that's a return address. So we need to know the return address. But right now we don't know what is the return address. The return address is where we put our shellcode. Then after that, we can place a huge knob sled there. And the instruction we're going to use is its ASCII number is just 90. That's the knob instruction. So after that, we have this piece of shellcode here, which is maybe 23 bytes, something like that. So to get a shell, we actually need to do a cat here. So we will keep getting the shell. So I gave you guys a reading to do maybe 2 weeks ago, explain why do we need this part. After this, we pipe the whole thing into this battery. So how do we get this return address? Any idea? We don't need to get the exact address, or maybe we cannot get the exact address. We just want to get some rough address. How can we get that? Basically, we want to find the address of this knob sled, or at least the beginning of here, right? Knob sled will be easier. Yes, we can. In this case, we can debug, right? We can debug, but like I said, when you debug, the address you get will be different than you run the program. But we can still try to debug this. So here, let's use GDB. We debug this program. We are trying to find the address of somewhere Overflow, right? Basically, we are trying to find the stack of Overflow. So we set a breakpoint at the Overflow, let's say. Then we just run this program. R is run, B is break. We run this program. So now we are at the beginning of Overflow. Then we just print what ESP has. So that is the address of the top of the stack right now. So GDB will add a lot of environment variables when you debug the program. So it will actually push the whole stack down without running this, using GDB. This address will actually be higher than this. Okay, but that's a rough address we can try. So if we get out of this, then the shellcode. Let me copy this. This is our exploit. There probably some special characters I need to fix. Not sure. When I copy this from slides. Okay. Let's say, then that 4 bytes of address, let's just use those address. So since we don't need the exact address, we can do something close to that. D6, FF, FF. So that's FFFF, which means that's the top of the memory space. That's the stack. Then we want to, this is a lob sled. The 90s are lob sled. Let's have a relatively big one. Let's have a 500 lob sled there. Then let's just try if it works. Okay. Okay. So here, that's a problem. Here should be C1. Okay. So when I copy it, there was some mistake. Okay, like this. Let's run this. What? Looks like we got lucky. Let's see if it works. Oh, it actually works. Okay, we got very lucky here. Let's use a smaller sled here. Let's say our sled is only 50 bytes. If our sled is only 50 bytes, to make this work, the return address has to be, there are basically only 50 possibilities, right? Anywhere 51 possibilities. Anyone in the lob sled or the beginning of 31, right? So the chance will be lower. Let's try. Wow, also works. Let's make the sled even smaller. Okay, so when the sled is very small, 10 bytes, you can see that doesn't work. We can actually debug why this doesn't work. Let's say, how do we do that? We can get the output of this. So this is our input, right? We put this into a temp file. Let's do that. So E means exploit. Oh, yeah, but when we use GDB, the address will be different. Oh, actually, we have that address. With GDB, it was 6C there. Okay. We put this output into this temp file. Then we debug this program. We debug this program. We set a breakpoint at the val_foo. Then we run this program. Now we want to redirect the input to this program. So we use this less than sign to redirect the temp E to this program. Now this program running, and we are at the beginning of val_foo. We want to say after val_foo, basically we want to, this is where we overwrite that return address, and when this function returns, we're supposed to get to where we want to go. So we set a breakpoint before the overflow. This is the address of gets, and this is where we're going to overflow things. We set a breakpoint here. Then we execute the program again, say continue. So now you can say we are about to execute call gets. So far the program is not, we haven't overwrite anything yet, right? So if we examine the stack, we can examine where EBP points to, because EBP points to the saved EBP. So this one I should use H or X. X. Okay. 4X. So maybe I need to do 8X or 8. I don't remember what's that. G or okay. G. 4G. Ooh. So how do I specify 4 bytes? Because the 4 here means 4 items. G here means, I remember it's X. No, not X. Okay. W. Okay. So now using this command, X means exam. And we want to exam 4 items. And each item will be 4 bytes. That's why 4W there. And where do we want to exam? Exam will only examine the address in a memory. The address we want to exam is at the wherever EBP points to. So EBP points to what? The saved EBP, which is also a stack address. That's why the first element here is FF D678. That's also a stack address. Then EBP plus 4 will be the return address, right? So you can say here the return address is 5655. That's where in the middle of the main function. Then after that, there are other items we don't really care about. So this is before override. Now let's do which command should I use? Step, call. Oh, you should use N. Next. Okay. So now we are at here. When I do N, will be a next instruction. It will execute this instruction and go to this instruction instead. And we know this instruction is a function call, which eventually triggers the buffer overflow. So when we do an N, now we will be at, we are at, the N actually jumps out of this. Let's say, should I do, it's better I set a breakpoint here. Okay, sorry about that. Let's set a breakpoint. Let's run this program again from the beginning. We set another breakpoint at where we return from the call. So now we, did we run? Oh, we did run, so we continue. Now we just return from, we have another, so we need to do say again. So we just return from gets, and the stack should already be overwritten. So let's examine the stack again. We use X4W EBP to examine the stack again. So look at our shellcode, export here. So what should be the value of saved EBP now? Will just be this, right? Uppercase A, which may be 31, 61, maybe 61 in hex. Then there will be 4 bytes of return address, whatever we gave there. So when we do this, you can see, it's 41. So uppercase A, 41. Then we have this return address, which is what we gave. But at that return address, do we really have the shellcode? Let's see. What we can do is we can examine again. Now we examine instructions. So will be I. We can examine 10 instructions. Then starting from the address of whatever we put there, for FF D6C. Okay, as you can see here, at that address D6C, it's not at the beginning of the NOP yet, right? The NOP started at D675. Before that, there are some garbage on the stack, but the GDB, the disassembler, will try to interpret those garbage. We'll try to say what instructions they are, but they're not really instructions. That's why several bytes here, they cannot interpret. That's why we have band here, okay? So when we return, we actually return to here. But if we return to anywhere this place, we only have 5 bytes here. Anywhere this place, we will be able to eventually execute our shellcode. So if you look at more instructions, let's look at 30 instructions. As you can say, after that, this is our shellcode, right? Tier the int 80. That's our shellcode. So that's why the exploit we have there didn't work. But we can make it work, like I said. Let's make the lob slider bigger. Also make this address bigger. We already know that. We can make it to 7 something, but even bigger. Let's make it to 90. Okay? Now we have a different exploit. So we debug this program again. We run this program with this input. Oh, I should set a breakpoint first. Let's break to Overflow first. It will be easier. Then we run this program. Now we're at the beginning of Overflow. We disassemble. Let's set a breakpoint after we have the overflow. We continue. Oops. We continue. So now we already know we overflowed that. Now we examine. Let's examine 4 bytes, maybe a little bit more. Let's examine 10 items at where EBP points to. Oops. What was the one I'm using? W? No? Not W? Okay. So X should be hex. Okay. You can say that the saved EBP, we override that with 4A's. Then we override the return address. Then we have a lot of knobs here. We have 100 bytes of knobs. And this return address, let's examine what it is there. We examine this. We do 10 instructions. Then at this address, I should not dereference, just this. As you can see here, right now, with this input, the return address is actually in the middle of the knob. So we keep going, eventually it will go to our shellcode, right? So then let's keep going. Let's keep executing this program. We execute this program with NI. So N means next function. NI means next instruction. So we should do NI here. So we do NI, several more. So we're at here. Now we are going to do one more NI. So now we are going to execute return. Okay. So now do one more NI. Then we are now previously we were executing in that .text section where compiler generated the code. Now we are executing directly on the stack, as shown here. And the instruction we are executing, you can just do I think disassemble doesn't work here. Disassemble requires, but we can do a X. Do a 20i from the current EIP. We disassemble from where EIP points to. And you can say that's a many lobs, right? We put 100 lobs there. We don't know. So if we put, we show 100 instructions, there could be, we should be able to say the beginning of our shellcode at some point. See? That's the beginning of our shellcode. So the CPU will keep executing each of those lob instructions and eventually execute our shellcode. Okay, so we don't need to go to the detail of the shellcode right now. We already talked about that last week. Okay, that's how we actually give the control to our shellcode. So if we run this, we just pipe this. Now this one. Let's make the lobs letter a little bit bigger. By the way, you can make it huge, right? You can make it 1,000 bytes to increase your chance. Let's say 1,000 byte works here. Okay, it works, right? Now we have a 1,000 byte lobs letter, or almost 1 KB. So now we have a shell. So with a shell, we can do anything, right? We want to just get the flag. So we just cat flag. However, it says permission deny. Okay, that's a problem. That's why this shellcode doesn't work. So why we don't have permission? This is a setUID program. The program we are trying to hack is a setUID program. So when we execute a new program by calling the exe cve system call, it looks like the new program doesn't have the root privilege anymore, right? So if you do a command like who am I, you can say you are actually CTF, you are not root. Okay, so this piece of shellcode works on Ubuntu 2 years ago. Okay, 2 years ago when I was teaching this class, this piece of shellcode works. So last year, Ubuntu changed a little bit. This doesn't work anymore. Other Linux distributions, they may have changed this long time ago. Okay, so other Linux distributions, this shellcode was not working for a long, long time. Okay. So how do we fix this problem? The reason it doesn't work is even if it is a setUID program, when it is replaced with a new program, the OS actually drop its privilege. So the only thing we need to do is to retail the program, retail the kernel. I want to maintain the root privilege. And that is done by another system call called set REUID system call. Okay. So this system call will restore the root privilege in case they are dropped. Some of the Linux distribution out there will not drop the privilege. But since Ubuntu is already dropping that, I guess many will follow. So what we have here is starting from this one, this part, that's our old shellcode, okay? This shellcode, which execute bin/sh. Before this piece of shellcode, those instructions, we are making two more system calls. The first one is number 31, which is get EUID. That's a system call which doesn't take any input. It will return the effective UID of the program. Then there is another system call we make is set REUID, which is real and effective UID. We set both. We set the real UID as 0, which is root. We set the effective UID as whatever we get there. So looking at this thing, we're actually making three system calls. The first one is get UID. The second one is set REUID. The third one is we execute this program again. So this will make our shellcode a little bit longer, almost 25 bytes, maybe 26 bytes. That's our new shellcode. Okay. So with this shellcode, let's try again. Remember that previously when we do who am I, our user is CTF. That's why we cannot cat flag. With this new shellcode, oops, can I copy it? With this new shellcode, let's say, here looks good. This is the address we want to change. Maybe 80, D6, I remember. D6, ff, ff. Okay, then sled, let's have a big one, 1000 bytes. Then we have our new share code. I need to fix the white space here. Let's see, looks good, let's see. Okay, now we can type something. We actually already have the share here. Let's say, oh, nope. So the address is not correct. So did we use D6 before? Yeah, here we use D6. Where? Oh yeah, I see that. Okay, try again. Okay, it works, right? Then now let's say, who am I? We are root. So now, because we are root, we should be able to get the content of the flag, right? That's how this one works. Make sense? Okay. Okay, so the two pieces of share code I just showed you, I call them share code because they are the traditional way they are supposed to return a share, and you can interact with the computer you hacked. You can run any program there. You can type any commands there. But for this particular challenge, you don't really need a shell, right? It's actually an overkill. Why do you need a shell? Your goal is just to get the flag. Your goal is just to read the content of a file. You don't need to create a new process, which is a share process, then type something, ask the share process to do something, right? So an easier way to do this, not necessarily fewer instructions, but easier way to do this is we do not use the EXE system call. We make other system calls. So look at here, what we have here is, let's see. We make an open system call. When we make this open system call, we didn't create a new process. So the old process still has a root privilege. And we open the flag file. When we open that, the file descriptor will be stored in EAX. Then we make another system call, which is send file. Send whatever in a file descriptor to another file descriptor. The first argument there, 1, what is that? What is 1? What is the file descriptor of 1? Why is 1? No. Yes, 1 is standard out. 0 is standard in, 1 is standard out, 2 is standard error. And when you create a program in terminal like this, actually all three, they point to the terminal, right? So here, we said 1 here means we are going to send whatever we open here to std out. And we are going to send the third argument is actually the offset. So we said offset was 0, so the beginning of the file. The 1000 here is the size we want to send. So this is not the typical way of reading and writing to read a file and output to a program, right? To the terminal. So any of you programming C, when you read some content from a file and output it, you probably use open first, same as here, use open. After open, you will use the read system call to do that, right? After read system call or some library call, then you will do a write and write to or you can do printf. Printf basically is the same as write. So the reason we're not doing that here is that will be one more system call. Open, read, write, right? It will be three system calls. Here, we only need 2 system calls, open and send file. So most of you are not familiar with the send file system call, but it does exist, okay? Another thing is, when you do an open read, you need to specify a memory area that the content is read to. Basically, you need to find a buffer to do that. Then you need to write whatever added a buffer to the std out. So using the send file system call, you don't need to specify the buffer where that is. The kernel will do that directly. So this piece of code, you can see we have 1, 2, 3 system calls. The last one doesn't really matter, exit. So we have 3 int 80 here. This is the first int 80. Let's see where's the second. This is the second int 80, and the third int 80. The first int 80 is to open this file. The string you see here, 67, whatever, that is the string flag. Then you set up the AL, which is a system call number. In this case, system call number is 5. Do I have a slide for that? No, I don't. Okay, let me just Google that. System call numbers, Linux. This one is good. This one actually gives us different syscall numbers for different architecture, x86, ARM, and also 64-bit. So right now we're using 32-bit x86. You can say the first system call we are making, it has the system call number is in the register EAX. So here what we have is number 5. So if you go to the table, you can say number 5 is the open system call, and it takes those parameters. The second system call we are making is here, and you can say EAX has a value BB in hex. You go to this table, you can say where is BB, BB. Okay, so that is the send system call. The send system call has 4 parameters. The first one in ECX is the output. Where should I output? This one probably in EDX. This one in, the first one is EBX, then ECX, then EDX. Okay, so BB here, let's say. So we need to set up EBX as 1 to indicate std out. Then ECX will be, in this case, actually, I think it will always be number 4, I guess. Yeah. Then the offset will be 0. The count will be, we're using 1,000 here. Okay. So here we open that. So let's see. We open that file. So in Linux or any Unix-like system, when you open a file, it will use the smallest available file descriptor available. In this case, I think it will actually be 3, because only 0, 1, 2 are used. std in, std out, std error are used. So this open, it will always return 3, okay? Or in most cases, it will return 3. So what we're doing here is after the system call, the EAX will have that file descriptor number. Technically, this part, we can hard code 3 there, I think, because it will always use 3. But if we do not want to hard code that, we just move EAX value to ECX. Then we set up everything else. We make the system call. Okay. So let's try this one. There's a white space I need to remove. Okay, maybe that's it. Where? Oh, yeah, D2. Yeah. Okay. Then this address, let's use a higher address. Let's use a very high address, maybe AA. So previously it was D6, right? Now let's just use E0. Okay, use a high address. Anyway, we're going to have a lot of lob sled. So make it higher, we'll increase our chances. Okay, when we do this, oops, I think it's because, okay. Did I type everything correctly? Maybe that's too high. We move from D6 to E0. Yeah, maybe that's too high. That's maybe more than 1,000 bytes. Let's move back a little bit to D8. Should work. Yeah. Okay. So when we move, so what happened is this number I was setting too big, right? So when I set a very big number, we actually return to beyond our share code, okay? Or maybe it's in the middle of our share code, but beyond the knob set. That's why it generates a segment fault set. So for that one, so if we use this high address E0, I think we can make it work. We just make the knob set even bigger. I don't know how big we need, maybe 4,000 bytes? Nope, maybe it's too. I'm not sure if the terminal allows us to do 4,000 bytes. 3,000 bytes still doesn't work. E0 is not that big, right? Okay, looks like E0 is quite big here. Let's say D8 works if we do DD. Let's see if it works. DD also works. But E0 is not that far away from DD anymore. So let's say DF. DD from DF is 500 bytes, right? Yeah, something like that. Okay, so DF doesn't work, which means this is not big enough. That is 500 bytes. Let's try. Wow. DF. So DD works. DE should work as well. Not much difference. Oh, even DE doesn't work. Okay. So we probably need to debug to say what's going on here. Sometimes the terminal doesn't really allow us to give so much input there. So this 3,000 bytes may not even work here. I'm not sure. But with some calculation, I think it should work. So here we have DD we tried. DD works. Oh, see? So when we use a smaller SNET, DD actually works, right? Remember we were using 1,000 and use that address DD, it works. So what was our input again? I remember the one was DD. Here. Oh, we're using D8. Oh, okay. We didn't really use DD. Okay, D8 works. So D8, because this one is, so when we move 1 from 8 to 9, we're actually changing 1 byte, right? So that's 256. Okay, so this sounds like big. Then it will be 1,000. So, okay, so 1,000 definitely not big enough. But 4,000 should maybe work, let's see. So let's try D9. D9 also works. So from D9, then we can do DA. DA doesn't work anymore. But if we move this bigger, because when we move from D9 to DA, we are moving 256 bytes. So if we make the knob sled also bigger, maybe 300 bytes, that should work. Okay, that works, right? So if we do DA, then if we do a DD, then change this to 3,000 bytes. Oops. Oh. we change this to 3,000 bytes. It doesn't work anymore. I guess that's because they do not allow us to go beyond the 3,000 bytes of input here. Okay, we need to debug to figure out. But anyway, you can say there are many different combinations you can make this work. So that's the 2 or 3 different shellcode we looked at. In this class, you are going to use this shellcode a lot. You are allowed to directly use those shellcode in the exams, in the CTFs. But you also will need to change those shellcode, especially in return-oriented programming, the second half of the class. You are going to write a return-oriented programming exploit that is equivalent to this piece of shellcode. Okay, so then let's move to the 64-bit version. The principle here is the same. Okay, it's just the shellcode we are using will be different. So 64-bit version, we do not use stack to pass the first 6 parameters. We use the registers, DI, SI, those registers. So the 64-bit version, if we disassemble that, we will find out that the buffer is at RBP minus 30 in hex. So the compiler also gave us 48 bytes of buffer there. However, the saved RBP itself will be 8 bytes instead of 4 bytes. So our shellcode, the very simple version of shellcode looks like this. This is just the exe cve bin sh. You can copy this piece of shellcode and you can compile it this way. Okay, this is how you can write your own shellcode. So when you write your shellcode, you do not necessarily need to write those instructions. You need to write those instructions, but this is an assembly file. In the assembly file, you can define a string, but this only works for 64-bit version. 32-bit, you cannot do this. You cannot do this, basically. Then we move 59 to RAX. That is the exe cve system call number for 64-bit. Then we set up several other registers. Then we do not use int80, we use syscall instead. So after you compile this program, you use GCC to compile it. You use GCC to compile, you use no standard library. You compile it as a static program. Then the output will be the shellcode L file. This L file will not have the C library functions. There is no main function either. Then you use the tool obj copy to dump the code section. Then you will get that several bytes you need. Okay, let's try this. Let's just copy this piece. Okay, cool. Let's just copy this piece of code here. So on this server, you can write anything in the temp folder. So let's touch a file in the temp folder, temp shellcode.s. Okay. So I think we have Emacs here. Let's see. Okay. So what I copied is just text. That's assembly language, right? So let's take a look if it is there. Okay, it's there. It's our assembly language. Then we need to compile that. Basically, that's some kind of source code. We use GCC to compile that. Why it looks weird? Okay. We use GCC to compile this. I guess we need to go to that folder, otherwise we cannot. Go to temp. Then we use GCC to compile this. The input is just s.s. The output will be the shellcode elf. So when we compile this, it's successful. You can say we have a elf file there. We do a file on this one. You can say This is a 64-bit executable. It's statically linked. It's not stripped. But if you do an obj dump on this one, so when you do an obj dump, the very first thing you say is, it's very small. When I do an obj dump, it only shows two functions, or actually one of them is not even a function. So all the other programs we dump, let's do an obj dump of the, where do we put the challenge? The root file system. The buffer, right? Okay. When you do when you do an obj dump of this one, there are so many other functions. Well, there is a affinity function, which we didn't develop. That's part of the C library. There are many other C library functions, like libc init. That's obviously a C library function. The main function is what we developed. Volfoo is what we developed. There are other functions, many functions. We didn't develop them. They're just part of the libc. So when we compile this one, we tell GCC we don't need the C library function, okay? Well, you actually, this part doesn't matter. You can't compile it with C library function. We're not going to use that anyway. So now we have this obj dump result. Of this file. Oops. What we really want is this part, you see? That's those instructions, those bytes are actually our instructions. So how do we extract that? The tool we use is called the obj copy. That's a tool, what's going on? That's a tool we just extract those bytes. We do an obj copy, then we are going to output to the file called shellcode raw. Then the input will be this L file. So when we dump this, now we have a new file here, which is, where is it? Here, this shellcode raw. Okay, so this is just it's not really compressed data. It's just raw bytes. Okay, so if we do a hex dump, you can see that. We do a hex dump of this one. That's basically our shellcode, okay? Maybe 35 bytes, something like that. That's our shellcode. Any questions? So that's how you can generate a shellcode and get the raw bytes. There are some online tools as well, maybe easier. So this is our 64-bit long share shellcode, which we will just do open the flag file and send the file, 2 system calls. You can see we have 2 system calls instructions. That's the first one. Second one, the last one is exit. Well, here I didn't put exit here. Actually, those 2. The first one is open. The second one is send file. But they have different system call numbers in 64-bit version. Okay, so let's try this one on our program. Go to 64-bit version. Oops. So we don't have an address yet, but we can fix this part. Let's have another big sled, maybe 1,000 bytes. There's a problem. Okay. Yeah, there's yeah, here. Okay. Then we more. Oh, okay. Oh, there's another one. Okay. Yeah, the multiple lines. That's why. Okay. Then we need to find the address. So we debug this program. We set a breakpoint at Overflow. We just run this program. Then we get a rough address there, ESP. X. Sorry, it should be RSP. Okay, so that's the address we have. So, now we use that address, maybe higher than that. Ooh, we need 8 of those. So last one doesn't matter. It's too small anyway. So E5, let's try E6. Then, oh, how many F are there? 7, right? 7F. Which means this is 7F, then 0, 0. Okay, let's try. We don't really, we directly pipe this into the program. Oh, it works. Okay, we're very lucky there. We use a big sled, so that's why. If we use a small sled or no sled, let's try 10 bytes. I don't think we will be that lucky, right? So we jump to somewhere, and the CPU say where you are executing. That's an illegal instruction there. Okay. So when we use a big sled, it works. Maybe even 100 will not work. We need to, yeah. See, that's how the 64-bit works. Of course, the 64-bit, we can also return a real shell, and this is the share code for that. So we're not going to demo this anymore. You will do this as part of your homework. The idea here is the same. Before exe CVE, you need to make those get EUID and set EUID system calls. Okay, that's the idea. Okay, let's take 10 minutes break. When we come back, we will do Overflow level 5. Then after that, we actually have an in-class exercise today. There is a program you guys will hack, and I will walk around to help you. That is part of your homework, but it's a little bit challenging, so I want you to start working on that here so I can help you. Okay, let's take 10. let's continue. So let's see what we have done here. Okay. So let's summarize a little bit how we were able to pull off this attack. So from attacker's point of view, from defender's point of view, I think it's always a good size to list all the conditions that attacker needs. So if any of you do research in cybersecurity in the future, this would be a very good exercise. You list all the conditions. Some of the conditions are very explicit, very clear. Some of the conditions are actually implied. If you can list all of them, then you think, what if I take out one of the conditions? Then the attack will not work, right? It may not be a perfect defense solution, but you make the attack more difficult to be put off, right? So then let's summarize the conditions we have been depending on here, right? The first ability is we actually put the shellcode onto the stack. There is a program running, and we were able to pull the shellcode onto the stack, which is in the address space of that program. And the stack is executable. The stack is supposed to have just data. But we put code there, then we're executing code there, right? Also, we have the ability to overwrite the return address and before a return instruction is executed, which means when that return instruction is executed, it will go to our place. Also, we have the ability to give the control eventually to the shellcode with a huge knob sled. So in the second half of today's class, we will look at other places we can inject the shellcode. We're not going to inject the shellcode in the buffer or somewhere near the buffer. We are going to inject the shellcode in environment variables and also command line arguments. So to do that, a little bit of background here is let's say how a process is started and what the stack looks like before we execute a process or a program. So as a C programmer, you start programming at the main function. And your main function will call many other functions. Even as a C++ programmer, the same thing, right? You have many different objects. The objects may have different methods. But eventually, there is a main function. That's where you, as a developer, you say that's the entry point of my program. But obviously, from the operating system point of view, that's not the entry point of your program. The entry point of your program from the OS point of view is a function called the underscore start. As a programmer, we didn't program that function. That's part of the C library function. Then that underscore start will call a C function called underscore libc start main. And obviously that function will call the main function eventually. So our main function can take multiple arguments. There is argc, it's an integer. There is argv, which is a 2-degree pointer. Then there could be another environment variable, which usually we don't use. We use a default one, right? So since the underscore libc start main calls our main function, so when that function calls main function, it will set up the parameters for the main function. So which means, so far, we are looking at the stack of a particular function. We're looking at the stack of the main function, the stack of the val-foo, but higher than that address, above that, there will be the stack frames of the libc start main function. There will be the stack frame for the main function itself. So let's say we actually have a demo here. There is a stack layout program. Do you see a stack layout program. Oh, here. Okay. Let's do a 32-bit first. So this is a very simple program. Where's my source code? Oh, I forgot to put the source code here. So basically, this program will print out, the main function of this program will print out the address of each argument and the value of that argument. Let's try. So when we run this program like this, there are 3 command line arguments. That's why you can see argc has a value 3. The argv is an array of address, which in this case will be at least 3, actually only 3 strings. The first string is the name of the program. The second string is hello. The third string is world. Then after that, we actually have environment variables. There are many more environment variables that the start main gave to this program. So we are only printing 3 of them. So the first one is like shell, bin bash, then hostname, blah, 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 current working directory, which is root /. So you can see their address, they are also on stack, okay? Very high address on stack, even higher than the address we saw for the Overflow or the main functions. So what really exists on the stack is something like this. This is where the main functions stack, and the main function has the first argument will be argc. After that will be several pointers. Will be argv0, argv1, argv2, then a null pointer, then the environment variables pointers. There are actually more than that. Then after that, that even higher address, those are the real environment variables. Okay? So those are the real environment variables. So we can run this on any program. We don't have to use this let's just run any program here and to show you what the stack looks like. So when we run this program, we do a GDB here. We debug this program. We set a breakpoint at the main function. Then we just run this program. Now, we just want to examine, because we know the environmental variables, they are strings, right? They are strings. They're somewhere on our stack. So we just examine maybe 100 strings on wherever the ESP points to. Okay. Let's say if we can get some interesting strings. So far, no, they are not meaningful strings, but we're moving up, okay? Then keep going. Still no. Not yet. Oops. Oh, we're on only 100. That's not big enough. Maybe 500. Let's try. Oh, you see? We'll keep looking up higher addresses and try to interpret whatever on the stack as the strings. And at some point, we find our environment variables. That's our environment variables, right? Those are our environment variables. Those were pushed onto the stack by the start main function or the start function, anyway, the C library function. Because when you run a program, that program wants to know what environment variables this system has and how those are passed. The C library passed that to the program by pushing those data at the very top of the stack. So if we get out of this, we just do a print environment variable. What's the command? Print this, I think. Yeah. So when we do a print environment variable, you can say those are our environment variables setting up in this shell right now. And all of them were pushed onto the address space of that program. What I'm doing. Okay, here. Okay, so the next example we're going to crack is this one. Still very simple program. Main function only calls Overflow. Overflow has a very small buffer, 4 bytes. Then there is a fget. It's just a get, but it takes from a file, not necessarily just std in. Then we're taking, but in this case, we're actually taking input from std in. And we are taking 18 bytes in, okay? So that's a program. And fget will read from string and store the C string. Actually, it will, no matter what it reads, it will append 2 characters at the end. One is OA in hex, one is 0 in hex. Okay. So 18 bytes here, let's say, this is a disassembly of the Overflow. C code level, we ask for 4 bytes. But the binary level, actually, we get is 8 bytes. You can see this is fget. The buffer's address is at EBP minus 8. Okay. Then the saved EBP is 4 bytes. Return address is 4 bytes. That is 16 bytes already. The fgets will append 2 bytes, A and 0, making 18 in total. Which means the input here is 18. You can input 16, and fgets will append those 2, making this 18. Which means you can only overwrite the buffer, which is 8 bytes, the saved EBP 4 bytes, return address 4 bytes. You can only override that 16 bytes. Okay, but the smallest share code we had before was 23 bytes, something like that. So not enough for us to input the share code. So how do we get the share code onto the stack or anywhere in the address space of this program? Right? So one way to do this is we put them into onto the in the environment variables. Okay. So this is that non-share share code, the same thing. I didn't change it. However, we're not piping this directly into the program. If we pipe that into the program, it won't work anyway. The program will not take so many bytes. The program will only take 16 bytes. So what we do is we put this into the environment variable. We use the command export. Then we say a name. The name doesn't really matter. It can be anything. So here I choose S code, equal sign. Then after that is how we generate this share code. We put this onto the environment variable in one environment variable, and we know that that environment variable will eventually be put onto in the memory of the program. So the next question is, if we put this in environment variable, how do we know its address? So most programs, their environment variable were at similar address. That's why we write another program here, which is a program called get environment variable. And this get environment variable program will print out the address of an environment variable. But it actually print out that environment variable's address in its own address space. Not necessarily the program you are trying to hack, but roughly at the same place, okay? Roughly. That's why we also want a big knob stack there, because we don't know the exact address. So let's try this. Wait, first, which one is this? Number 5. Buffer overflow return 5. 32-bit first. actually here be easier. What do we have here? Let's see. Okay. So now we put this into, so we can do how do we? Oh, we can do an echo $S code. Then will show us the value of that string. Of course, a lot of characters are not printable. That's why we do not say them. So now we put this shellcode in environment variable. Then we want to overflow this program. So this program, let's see, how many bytes? We're inputting 16 bytes, right? Let's see. Oh yeah, we're inputting 16 bytes. So this 8 byte doesn't matter, this 4 byte doesn't matter. What matters is this. This one has to point to the knob sled on the stack. We don't really know the address there. Then let's make the knob sled even bigger. Maybe let's do 2,000 bytes. Okay. So after that, we can do Python 2 print. So here we have 12 bytes, right? So we put 12 bytes there. Then we just need the address. Let's just use the address we tried before, like 00D6 FF. So we will go from here. What did I do wrong? Yeah. Okay. So that's basically our input, right? So 16 bytes of that, then the address. Ooh, there's a 0. Oh, okay. I guess that 0 doesn't matter because we're using fgets, so it doesn't really matter. Okay. Let's do this, segment fault. Then maybe we can go to a higher address. Ooh, we got lucky, right? So in this case, in this command, we didn't inject the shellcode. The shellcode was put in the environment variable. And when that program executes, the C library, or so OS, whatever, whoever, put that environment variable in that program's address space. So the shellcode, we still inject the shellcode onto the stack. Then when we run this program, we just need to jump to that shellcode. And we guessed here, and we get lucky here because we have a huge knob sled here. Okay. So that is how we can put that in environment variable. Another place we can, actually, well, I forgot to show you guys the tool. I simply guessed where it is. You can actually use a tool. We already installed the tool here. That's just a simple program we developed, 32-bit. Then you put the name of that environment variable here, S code. Then it tells you it is roughly at, it's actually at this address for this program. It may be a little bit different for the program you are trying to hack, but close. Yeah, so you can say if it stays here, that's why this one doesn't work, because the address is lower than the knob sled. And this one will jump into the middle of the knob sled. This one is D800, this one is D600, the address is D6C4. That's the reason. Okay, so there is another place we can, where's my slides? Weird. Okay, I guess maybe I put that in next class slides. So basically there's another place we can put the shellcode. It's just command line arguments. We just put that as a command line arguments. Let's see if I can do it here. How do we delete environment variable? Anyone remember? Unset. S code. Okay, let's try again. Okay. So now we don't have S code. We don't have an environment variable like that. Okay. Now we can simply input that as a command line argument. So what does that mean? Let's say we just run this program. Let's say, okay, let me copy this part. So this is a program. Okay, so this should not work anymore, right? Because we don't have the shellcode. So now when we do this will get a segment fault or illegal instruction, right? Because we don't have shellcode there. So now we can run this program and we put this one here. We put this part here. So how this works is, first we are going to run this part. It will have our exploit. Then we are going to run this program. But before we run this program, we need to run this Python script. And this Python script has some output, and that output will be used as a command line argument for this program. So we still get the shellcode onto the stack, right? So let's see if it works. Oop. That's easy. The first try. Well, our sled is really big. If we make it 200, or that's 200. Oh, even 200 works. So this address we put here is perfect. So if we put DE here, it should not work, right? DE is maybe 400 bytes higher than this, so it should not work, right? Yeah, so you can see there are many ways we can inject the shellcode into the address space. Okay, that's basically the lecturing part of today's class. Next, we're going to do something fun. Okay, so this is a program on over the wire. So over the wire is, I don't know anyone here heard about this? There are many challenges on over the wire. Some of them are very simple ones to just do Linux commands. Then there are a lot of byte-erase challenges as well. So we're going to play the Behemoth level 1 of over the wire. And I gave you the credential here. You can, no matter which machine you use, you can SSH into their Behemoth machine, and here's a password. Okay? Then your job is so their setup is similar to our setup. There will be a program called Behemoth 1. That is a program you are going to hack. And that program is a setuid program. When you hack that program, you will have the privilege of Behemoth level 2. And with that privilege, you will be able to read the password at this address. And that's what you are going to do. You are going to read the password at this address. Okay. So how do you approach this? First, you need to find out what kind of vulnerability Behemoth 1 has. In this case, buffer overflow, obviously. Then you need a shellcode that works. Either gives you a share directly, so you can do a cat, this, or you have a long shellcode we had before. You change that shellcode. So the long shellcode we have will read from /flag. You can change that shellcode to read from this file directly. Okay? Either way is okay, as long as you get the flag here. If you want to have a template for shellcode and compile, you can download the slides from my website, and there are commands for you to use. You can copy, paste, and run those commands so you can get your shellcode. Or there is also a very good online tool you can use. Okay, cool. Then I will walk around and to help you solve this one. So this is part of your homework. This week's homework will be a little bit challenging. Let me show you the homework first. There are several challenges that I didn't demo in a class, and you need to solve them. Task 1, 2, I demoed. Task 3 is the one you are going to do. I'm here to help. Task 3, oh, I have a typo there. Ooh. Okay. Task 4, you are going to crack a program called Crack Me. Then you need to crack the 32-bit version and the 64-bit version. And this is the first time in this semester we will have a bonus question. If you get this bonus question, you get 15 points more. So technically, the total for this homework is 60 points instead of 45. So a little bit hint is Crack Me 4 and Crack Me 4H. H here stands for hard, difficult. They compiled from the same C program. However, they were using different compiler optimization flags. And this version, it's harder to crack. It's more complicated, even though it's from the same C program. Okay, you can start with behemoths.